Hello everybody. This video is about the exploratory spatial data analysis using PySAL with Jupyter Notebook. First of all, I would like to sincerely apologize to all my subscribers for my very long absence due to illness. In fact, I posted my last video. It was in November of 2024. This year, the year 2025 is still at some point difficult for me. I suffered from deficiencies in vitamins, especially B12 and B2, as well as in minerals such as magnesium, calcium, and iron. I'm recovering now, but I'm still convalescing. With God's grace, I will try my best to post at least a video every month. Thank you very much for being my faithful subscribers. I wish you a joyful Christmas season and a prosperous New Year 2026. Please, if you could, your generous donations and compassionate thoughts are very welcome. This is my email address. It's also linked to my Zelle account. So thank you very much. Let's go to the purpose of this video, which is the exploratory spatial data analysis using PySAL in Jupyter Notebook. So you first need to install libraries, so either in terminal or another prompt or command prompt. So you install pandas, install GeoPandas, install PySAL, the library needed for this work. You need also Folium. At some point, we may use Seaborn also, and need NumPy and Splot. So after installing them, you need to import them. This now is in Jupyter itself. So we come to the cells and we import the libraries. For tabular, relational, or label data, you need to import pandas as PD. For generic math, of course, it's NumPy, SNP, to import it. And then for just spatial data management, we need to import GeoPandas as GPD. To perform special operations, we need from shapely.geometry, we need to import point for coordinates or spatial data. And then we need to import PySAL for the spatial data science. This is the required library. And from PySAL.lib, we need to import weights to define neighboring observations. From PySAL.explore, we need to import ESDA to test for spatial autocorrelation. From ESDA.moran, import moran local to test for global and local spatial autocorrelation. We need to import Folium to visualize in a left map. We import splot for status plot, interactive visualization, and special data exploration. From splot.esda, we import Moran scatter plot, plot Moran, Lisa cluster, plot local autocorrelation. And from splot.libPySAL, we import plot special weight, plot the special weight. Seaborn as SNS. For graphics, we need to import matplotlib.pyplot as PLT. And at some point, matplotlib.colors as colors. And sometimes we got the result, the float result, as np.numpy.float 64 in parentheses. You have the result. This is related to the version. So to prevent this from happening, we type this code np.set underscore print options legacy equal 1.25 quote. And to prevent warning messages from happening, we import warnings, then warnings dot filter warnings parentheses in not in quote. So let's run, call the libraries, and then warning messages, suppress them. So this is the data set, I call it wells, equal gpd.read file. This is the directory where the file is found, vdata, sdata, and the name of the data set. It's a shapefile, kim area. Let me run it. So let's see the first 5 rows of our data set. So this data has the physico-chemical properties of the wells, water wells. So we have the coordinate x and y of the wells. We have the total depth, h at the end, and the sulfate, the nitrate, the pH, the temperature, and the conductivity, the electroconductivity. And here is the well ID. So let's have the basic statistics. Wells dot describe. It's to describe what we have. Our file is a shape file. We need to transform it into pandas data frame, then to pandas data frame. So let's go transforming the data set into pandas data frame. Wells data frame equal pd pandas data frame wells so let's see the head and df dot head so this is what you get. Geometry is still none for the wells, as well as in the shape file you have That's where it's important to have it in geodata frame. To transform the pandas data frame into a geo data frame. For this we need the geometry. Let's set the geometry. Sorry for the typos. Geometry equal point xy for xy in zip parentheses wells data frame dot x coordinate wells data frame dot y coordinate. This is setting the geometry. Then transforming the geodata frame will have wells geo df geodata frame equal geopandas dpd dot geodata frame parentheses wells df or geopandas data frame. Then we have the geometry. So geometry equal geometry like that. Geometry equal geometry in the coordinate reference system. We set it to EPSG problem 4326, and this should be in quote. And then close the parentheses and we run. So let's print our wells geodata frame dot head, and let's see what it has. So we have the geometry point. So each well has its coordinates, x and y coordinates. We have the points here. See here, same as one here. So now you can go ahead and perform some geospatial analysis. Otherwise, with this you cannot. With pandas data frame you cannot, with shapefile only you cannot. So to transform, instead of transforming. Okay. So let's plot the spatial distribution. Our data of interest is our variable of interest is pH. potential in hydrogen. For this study, we are interested in pH here. So rows. Let's have the special distribution of pH. Values. Distribution. Okay, we have a fig AX. We define the figure, the size of the figure. Fig, comma, X equal PLT dot subplots the fig size equal to, let's have 12 and 10. Then let's have the plots. Well, DDF wells DDF dot plot. We are interested in pH, so column is pH. pH. And then AX equal to AX. Then I have 20 dot show. So it's running. Okay, so this is this special distribution of data. We'll reduce a little bit. Along the altitude and the longitudes. Okay, now let's have plotting the chlorophyll map. Of pH. We are exploring it. Wells DF dot explore parenthesis. Let's put this here as well. Okay. Text equal Picato dB positron. comma, column. We are interested in pH. Height. Equals 60%. Width equal 60% as well. Skin equal natural breaks and cement equal orange is then style underscore KWDS equal have a curly bracket. Let's close it. Stroke set to true. Edge color set to K. Line width go 0.03 and the fill opacity one. And then come out of the curly bracket here. Legend underscore KWDS. Set the legend. Have curly bracket again. Here color bar false. If you want color bar, you put true. Have your font here. And because the put here curly bracket close here and the parenthesis close here. Let's run the code and see. Enter and make this string 17. Okay, let's see here. I got the syntax. Problem. Okay, you can see. One here. There's problem here. The code is after 60%. Okay, it's running. Let's see. That is easy. So, map is not coming out yet. So we run one more time. Okay, sorry, the map is not showing. This is the code. Normally it should show. Maybe it will take more time. Okay, so let's continue with building the special weights. Object for contiguity base neighbors. So we have W for weight equal weights dot contiguity dot queen dot from underscore data frame, and we have our object which is where's DDF. Okay, so now let's visualize it. So plot special weight. W and the wells T then plenty that show. For this time we have it. Okay, this is the special weight plot here. Then you need to see which tracks are neighbors of which. So basically we transform weights into binary. So transform W transform here is code P binary. This is the first thing we need to do. One means neighbors, zero means not neighbors. Again it means not neighbor. Okay. Then we show neighbors, neighbor indexes. Let's put it. Let me put it here. So the same line. So W dot neighbors. This is to show neighbor indexes. Neighbors indexes. Okay. These are the indices of the neighbors of the observation 0, observation 1. These are the indices of the neighbors, and so on, up to down. Then to show each neighbor's weight, w dot weight. These are the weights. Above we have indexes from the weights. So now I'm going to calculate special lag. Calculating so else geodata frame, of course. We need our variable of interest weight, so weight of pH equal weight dot lag underscore special parenthesis w wells geodata frame the variable of interest pH. Incomplete input pH here. P. Make parentheses to close here as well. So let's go and see in the headers of our geodata frame. You see that WPH, the weight of pH is added. WPH. Because we add this here. So these are the weights. Okay. If you want to see this is to add our new variable WPH to the geo data frame. Now if you want to do the same with the wells ID, so have a wells GDF geodata frame, have parenthesis, you now add no parenthesis code bracket twice. The second is to add the well ID. Close here. Then we have pH. Then we have the weight pH. I hope everything is closed. Let's have the head. This. So this is what you have. So we basically extract only the 3 columns: weight here, WID, and the pH itself. So to see the weights of the neighbors of indexes, of the indexes you have. Let's see. Let's go to the global spatial autocorrelation. Our variable of interest equal pH, so we have wells GDF. We take pH, then calculating Moran's statistics. Moran equal to Moran Y W is the Moran statistics. Outputting Moran statistics. So Moran, instead of Moran. Take Morans. This the correlation here, 33, 0.33. Now we need to output the p-values to verify the statistical significance of Moran's statistics. P underscores statistical significance, so 0.01, 0.001, that's p-value, way lower than 5%. So let's plot plotting Moran's statistics to help visualize the correlation. Problem with my keyboard, typing R. we plot the scatter plot here. Fig AX equal Moran underscore scatter plot parenthesis Moran aspect underscore equal to true. Then if you want to save it, plt.save fig scatter, we give it a name, scatter dash Moran dot png, for instance. Then plt.show so Moran scatter plot. We have the correlation here, the special lag, and the attributes here. So let's go to the local autocorrelation. So this is the global autocorrelation. Calculating local Moran. M underscore local Moran equal to Moran underscore local. You have Y W and then p-value plotting local Moran first. Fig x equal Moran scatter plot M local Moran local, and we have the p-value we set to 5%. We set the X label special X pH. This is pH. Y label. Special lag of pH. Let's run and see the type goes progressively. which line is it? Okay. So we have now to put the test plt dot test the text it's 0.5 2, then high, then font size 25. Then same thing, plt.text. Now we will have low, high and low. So let's see, 1.95 for x, negative 1.5 for y, and you have high, low. Font size the same. Have again plt.text. Now for low and high, so negative 2.5 and 1. Have low, high, font size the same. And the plt.text for low, negative 1.5, negative 2, so low, font size the same. Okay, let me verify. 0.5 2, font size 25, and 1, 95, negative 1.2, 1.5, sorry, high, low, and the plt.text, negative 2.5 and 1, x-axis for low, negative 1.5 and then negative 2. Okay, and then you have a plt.show. So let's wait a little bit. Hopefully this one is okay, we have it. So these are the coordinates for x and y. So let's say low is here. You have negative 1.5 x low here. So x here, we put it here. Negative 1.5, negative 2, y, negative 2, around here. Just to move these around. The letters, the text, you have y x equals 0.5 somewhere here, and y equal to somewhere here to put each. That's all. So this is the Moran local scatter plot. Here, if you want to plot the map with local Morans classification to identify Lisa cluster. fixed size, say let's put 10.8. I think that supports. If the command fig px, then I have laser cluster. So okay, I see it's comma here instead of a dot. I'm sorry. Instead of 10.8, it's 10,8. Okay, sorry about that. Then you have Lisa underscore cluster, and then M local, sorry, Warren local, then Wells geo data frame, then p value equal to 0.05. Then let's have that's inside again. Fixed size equal to, let's say, 10,8. Not pointing at this time. And ax equal to ax. Then plt dot show. And my syntax here, sorry. Okay, this is the map showing the locations of high, low, the distribution of the values of P8, depending whether they are high or low, the cluster system based on laser. So now let's drill into laser itself. So we will have again this map, but in another form. So calculating laser. Laser equal to ESDA dot Moran for local wells geodata frame, our variable of interest, which is pH, and then the weight. So this is result calculated already. Now we need to break observation into whether they are statistically significant or not. If you want this, statistically significant or not significant. So our object, well, GDF. Significant equal Lisa dot P underscore sim less than 0.05. Sorry, capital letter, press cap lock is on, so yes, that's what I see. Okay, now we need to see the first 5 rows of our significance observations. That's DGF. Dot head. Still running. My computer is very slow. It's busy now. Significance here. So it's typo in significance, noun significant. Yeah, this is what you get. So only the second observation is significant. It has less than 0.05 p-value among the first 5 observations. So we can check the p-value. Checking the first 5 p-values. That's a boolean. It gives us false or true or false, but now we are going to see the p-values themselves. So we have Lisa dot p underscore sim, and we have we ask for the first 5. So we see here true, so less than 5%, here true. The others are false, so greater than 0.05. Okay. let's store the quadrants to the observations they belong to. Nice. DDF quadrant. Equal Lisa dot Q. We need to verify the quadrant each observation belongs to. Just ask for the first 5 rows. Where's DDF? Quadrant dot heads dot head. So the second column here is quadrants. So the quadrants are from 1, 2, 3, 4. And these are the observations. So we have quadrant 2 with observations 0 and the index of the observation, yes, 0 and 3. Quadrant 1 has observation 2, quadrant 3 has observation 1, and quadrant 4 has observation, no, quadrant 1 has observation 4. Okay. So let's plotting the Lisa cluster map. Lisa underscore cluster parenthesis Lisa Wells DDF, and then PLT dot show. So this is the Lisa cluster map. It's the same as the one you have here. We got it here. Now we are going to put the 3 maps together to have an holistic for general observation, global observations, global observation for visualization, global visualization of one local plot connected to Lisa statistics in the pH. Statistics in the pH spatial distribution. Distribution. So PLT dot local dot auto correlation Visa Wells DDF then pH. Then PLT dot show auto correlation laser here. Okay, let's see. Plot instead of PLT. I'm sorry. Plot local auto correlation. Okay, so this is what you have. So you have more on local scatter plot here. You have laser statistic here. And you have your pH, or pH spatial distribution. So you can see how they are connected depending on the quadrants here up to here. So this is the end of the video. I'm sorry for the typos, and yeah, my computer is also old, so I'm having problem with the keyboard, so I have to press hard to get some letters. So I hope this video will help some people while doing the research to explore their data. I'm sorry for the map that did not show. I hope it's already shown. Not yet. It's still not yet. So thank you very much for watching, and see you next time for another video. As I said here, I apologize, and now I'm going to do my best to come to post a video, to be ready for a video, at least a video every month. So thank you for watching this video. See you next time.